Hey, good morning. So we completed the lecture 6 for the artificial initial solution, the two methods. We went through the second method on Monday, which is called the two-phase method. And we explained that this is another strategy for you to find an initial solution for problems that have constraints in which you will not be able to find an initial solution quickly, like the cases we studied at the beginning, in which all constraints were less than or equal to. So we studied the M method, and also on Monday we went through the two-phase method, and I want to quickly go over this method again, just to review it and then see if we can work on the lab that was assigned for today. So let's go through it. If you have questions, now's the time to ask those, and then we will have that practice. And then on the second portion of today's lecture, we're gonna start a new topic. This will be the last material that will be included for the second exam. We're gonna talk about the sensitivity analysis in linear programming. So we will see how far we can go in that material. And then on Monday, we're gonna have our review for the second exam. And on Wednesday next week, we're gonna have our second exam. So on Monday, I'm going to bring the instructions for the exam. I mentioned the possibility of having an online or a mix of online in-class exams. So I'll bring those instructions and that information on Monday. So let's go through the material for today. So again, the two-phase method is a second strategy to find an initial solution for linear programming models before you apply the simplex method for those problems that have constraints that are greater or equal to or equalities. So two-phase method, the name basically state what we are trying to do. We have a first phase that is trying to find the initial solution for the problem. In this first phase, we are trying to formulate a problem that uses artificial variables. And the artificial variables, the objective function is going to be formulated in a way that we're going to minimize the summation of all the artificial variables. We solve the problem, and at the end, if we find out that we can find an initial solution without the need of the artificial variables, meaning that these artificial variables are non-basic, or if they're still basic, they have a value of 0, then that means that we can find an initial solution for our problem. So we take that solution or that tableau to the second phase. In the second phase, we are bringing back the original objective function into the problem, and we bring the coefficients from the solution of the first phase into the tableau. We need to make sure that the second phase tableau is consistent with the solution. So we have to perform some elementary row operations before we apply the simplex algorithm and find the solution for the problem. So, so we went through an example in class. This example right here, we have constraints that are equalities and greater or equal to. We also have a constraint that is less than or equal to constraint. And then we first step is to set up the problem into equality form. So we are subtracting the excess variable on the second constraint, and we are adding a slack variable on the third constraint. And then, as I mentioned already, in phase one, we attempt to find the starting basic feasible solution for the original problem. And we're going to be replacing the original objective function, regardless of whether it's minimizing or maximizing, with the minimization of the summations of the artificial variables, which is the objective function that you see that in that last bullet. So after replacing the objective function in phase one, we are also going to add artificial variables to those constraints that were equality or greater or equal to. So in this case, we have two artificial variables. We don't need an artificial variable for the third constraint because we have a slack, so we can use that. And then if we set up our basic variables to be R1, R2, and S1, we make the non-basic variables X1 and X2. We can find an initial solution for this problem in terms of R1, R2, and S1 being equal to 3, 6, and 4. So before we get into solving this problem for the first phase, we have to make sure that the tableau is consistent with the solution of the problem. So we are saying that R1 and R2 are equal to 3 and 6. So when we look at the objective function value in the initial tableau, we get a 0. So we know that's not consistent with this objective function. It should be 3 plus 6, should be 9. So the reason why it's not consistent is because we have to make sure that these values here in row 0 for R1 and R2 should be 0. So they are part of the identity matrix. So only a 1 is allowed in that column, and then the rest of the column should be equal to 0. So we perform the elementary row operations to make this value 0 and this other value equal to 0. So before proceeding with the simplex method computations, our row must be made consistent with the rest of the tableau. So we perform this elementary row operation, and then we obtain this new tableau. So you see now the objective function value is consistent with what we have in terms of the solution for R1 and R2. So 3 plus 6 equals 9. So at this point, we are ready to apply the simplex method. So all we did at this point was to set up the tableau in the right. So we are minimizing. The objective function is the minimization of the summation of the artificial variable. So we are going to look for the largest positive coefficient in row 0. So in that case, that's X1. So X1 is going to enter, and then we do the minimum ratio test to identify who's going to leave. So that's the operation that we are doing right here. So the minimum is 1. So that means that X1 is going to enter, R1 is going to leave. So after performing the pivoting and the elementary row operations to transform the column for X1 into a column that resembles R1, this is the new tableau, the second table. And at that point, we have to again look at the row 0 and make sure that to identify whether or not this is the optimal solution. We find that there's a positive coefficient still in row 0, which is 1.7 for X2. So X2 can enter the basics. We perform the minimum ratio test again, and we find that R2 is the minimum. So R2 is going to leave. So now the column for X2 has to resemble the column for R2 in that second tableau. So we perform the elementary row operations. And then for X2 in the third table, we get the 0010 column. And then at this point, we check row 0 again, and there's no positive coefficient. All coefficients are zeros and negative values. So we are done. This is the optimal tableau for phase 1. And this is an initial solution for our problem. X1 equals 3 over 5, X2 equals 6 over 5, S1 equals 1. So what we do at this point is we take the coefficients for the solution from phase one. We can eliminate the artificial variables from this tableau because they have completed their purpose. They're no longer part of the basics. And since because the minimum R equals 0, phase one produces the feasible, basic feasible solution, as we stated already. X1 equals 3/5, X2 equals 6/5, and S1 equals 1. So again, at this point, the artificial variables have completed their purpose, so we can eliminate those columns and then proceed to phase two. Yes. Yeah, so basically the question is, why do you want this column to resemble R1? Yes, so you see the basic variables, these are our basic variables, meaning that these are the variables that are giving us a solution for the problem. So in this first tableau, that solution is given in terms of R1, R2, and S1. So if the variables are not listed in this column, what that means is that X1 and X2 are currently equal to 0. Okay, so if there are no basic, so in these three variables right here are basic variables, the rest are non-basic. So all non-basic variables are equal to 0. So what we are saying, okay, I need to know if there's any other variable that if it becomes basic, meaning that it becomes a value different than 0. If I do that, my solution will improve. So that's basically what I'm trying to find out. If from this group that is equal to 0 right now, the non-basics, can I bring one of those to the basics and then say and then check if I can get a better solution? Meaning that variable is no longer equal to 0, it could be a different number. So the way you do that is by replacing. Okay, so you need to know which variable you're going to replace in order to bring a new one to the group. So since you're identifying R1 as the variable that is going to leave the group, so you can bring X1, then you need to make sure that when you replace X1 by R1, X1 is taking the place of R1, and the way that you do that is by making sure that this column represents this column now. Okay, so the basic variables basically are represented in the tableau by having columns that are 1, 0, 0 or 0, 0, 1, 0. So they are part of the identity matrix. So that's why every time you decide who's going to leave, you need to make sure that that variable that is entering the column resembles the variable that is leaving. Okay, so we did the same thing here for X2. So X2 is entering, and then R2 is leaving. So that's why we want X2 to resemble this column for R2. And that's what we did here in the third tableau. So moving forward, we now use the coefficients from this tableau to state the new problem for phase 2. You're bringing back the original objective function, and we are using the coefficients from row 1, row 2, and row 3 to state the constraints. These constraints are going to provide us with the initial solution for the problem, for the original problem. So phase 1 has transformed constraint equations in a manner that provides a starting basic feasible solution for our problem. So to now solve this new problem for phase 2, we're going to use the coefficients from phase 1, but now we the objective function from the initial or the original problem. So when you set up the tableau for the phase 2, you will observe the same problem that we have for the phase 1. We need to make sure that the row 0 is consistent with the solution for the problem. So the solution is the value for the objective function value is always this value at the top right. So in this case, it's equal to 0. But you know that if you substitute X1 equals to 3/5 and X2 equals to 6/5 into the objective function, that is going to give you a value that is different than 0, which means that this tableau right now is not consistent with the solution of the problem. So if you remember, every time that that's the case, we don't have a solution that is consistent, is because when you look at the identity matrix in the objective in the tableau, there's a value that is not 0. So in this case, in row 0, those values should be equal to 0. So we need to make sure that those values are equal to 0 by performing the elementary row operations. So that's what we're going to do to make this tableau consistent. So again, we perform these elementary row operations. We make these 0 and 0, and we obtain the z value that is corresponding to this solution: x1 equals 3/5, x2 equals 6/5. So at this point, the tableau is now ready for you to solve using the simplex method. So in this case, we are still minimizing. So we find the largest positive coefficient, which is E1. So we enter E1, and by application of the simplex method, we will complete the problem after completing this iteration. So the solution is not shown, but you will find the solution by entering E1 and finding the minimum ratio test. So being S1, so after completing that iteration, you will find the optimal solution. So that's the two-phase method. What I want to now, any questions? Yes. Yes, so that's a very good question. So basically, what this means, in mathematically speaking, is that for that constraint, it doesn't matter the value for E1, because it's not going to impact the solution of the problem. So when we find a negative value, we don't worry about that one. If you go back to the explanation of the simplex method, you will see that we were solving and making sure that what is the minimum value that this decision variable that is going to enter can have, so we don't get a negative value for the other variables in the system. So basically, what this is representing is, for this constraint, second constraint, it really doesn't matter what value E1 is going to have, because it's not going to impact it's not going to make the other decision variables negative for that constraint. So we don't account the negative values. We don't when it's a division by 0, I think the undefined term is what's confusing. Undefined is only when you are dividing by 0, so that's always undefined. This will be not impact the solution. So we don't take that into account. Negative values are not considered. We only focus on those values that are positive, because those are the variables that are going to be impacted by having this new variable entering the problem. Okay, good question. So now I want you to try to work on this lab. So I have hard copies, actually. I'm going to pass those around here. Oh, yeah, sure. So maybe form, that's what you call standard form? Yes. So you set up the problem with all constraints in equality form. So you add the slabs or subtract the x's variables. And if you're working from or watching this video from home, the exercise is available in the modules. Lab 8. Oh, okay, yeah. So, what's happening?
Are we gonna have to do both of these methods on the test?
You'll be asked questions about each method, but I'm not gonna ask you to do the whole thing. Yeah, yes. You can just name it, as long as it's an artificial variable, you can give them any name. I name it R2 because it's in the second constraint. Okay. Yeah, so going back to the exam questions, it would be more complete this piece or what would you do next? Those type of questions for these methods. No, it's an actual problem. It will be an actual problem for each method. But for example, I can give you can ask you to set up the problem into standard form and then develop the initial tableau. Complete the first iteration, something like that. Because that basically tells me if you understand the method or not. I'm more interested on finding out if you know how to get that initial solution. Because the rest is just the application of the simplex. Is the objective function value for the phase one objective function. So instead of little z, we use little r because it's for phase one. Yeah, this second exam is about the simplex. So do you know how to find a solution using the simplex method? If you have all less than or equal constraints, do you know how to apply the simplex method if you have constraints that are equalities or greater or equal to? So you have to apply the artificial variables and one of these two methods. And then can you solve a problem using the computer? So it's about solving problems, this second exam. But in terms of solving the problem by hand and then solving the problem in the computer. Okay, so the first part is asking you to put the problem in equation form, add the necessary artificial variables, and formulate the problem for phase one. So if you did that correctly, you should have an objective function for minimizing R2. And then the first constraint should have a slack variable. and the second constraint should have an artificial variable and minus an excess variable. And then don't forget to make all those decision variables greater or equal to 0. Yes. Yes.
Yeah.
So the question, do you have a specific question, or is it about the name, or?
Yes.
Well, R, it could be R1 or it could be just R. I'm naming it R2 because it's part of the second constraint.
Oh, so we have the
You have 3, then you have R1, R2, and R3. Yes. So this is just a name that I'm giving that variable because it's part of the second constraint.
mentioned that just to make clear why we have our second constraint.
You don't need an artificial variable in the first constraint because that is a less than or equal to constraint. So you add a slack variable, and if you add the slack variable for that constraint, you already have the piece that you need to find an initial solution. You remember our first examples were all less than or equal to constraints, and we were adding the slacks, and we were able to find an initial solution just with the slacks. Why is that? Because if you make the slacks, all of them basic variables, you make the rest of the problem non-basics, basically the x1, x2, x3 decision variables, you make them equal to 0. If you make them non-basic, then you can find a solution, a positive solution just with the slacks. But that's not the case. If you have excess variables, you will not find an initial solution that with positive values because this is a negative coefficient. And then if you don't have a slack, or if you don't have a slack, like in inequality, you don't have a slack, then if you set up your x1, x2, x3 values equal to 0, then you don't have a group of variables that you can assign to the basics. So it will give you an initial solution for your problem. So what I'm trying to say is, if you have a slack, that constraint is already having a decision variable that will allow you to find an initial solution for your problem. But if you don't have a slack, then you have to go and use the artificial variables to be able to find that initial solution. So in a problem in which you have a slack variable for every single constraint, you don't have to use the artificial variables. Artificial variables are only used when you have constraints that are equalities or greater or equal to. Yes. Have a question?
Yeah, I was asking about like we have the minus p.
Yes.
I know.
No, it won't, because basically what this is saying is that all your decision variables must be greater or equal to 0. So even if they're subtracted in the constraint, you can take a positive value to that decision variable. Basically, what you're going to do is, if it is positive, you're going to subtract it in the constraint. If it is a negative value, we don't want that. We want them to be positive. So all decision variables must be positive. Yes.
The first row, shouldn't it be R2?
Here?
Yeah.
Well, in the formulation,
R2.
yes, that's when you set up the tableau. Yes. So not getting confused. The formulation is minimizing the artificial variable. Wait, when you so the formulation is, let me turn off the control. So minimization for phase 1 is the minimization of R, in this case, R1. Maybe it's a photocopy. I think it's not looking very clear. Yeah, so that objective function should be minimization of R when R is R2. If you have more than one decision variable, then this will be the summation of all your R's. So if you're in your formulation, you end up with two artificial variables, one for the first constraint and one for the second constraint. This would be R1 plus R2, right? But in this case, we only have one artificial variable. It's always the minimization of R. Yeah, it doesn't matter if the problem is maximization or minimization, because what you're trying to do is to find an initial solution for your problem where the artificial variables has a value of 0. Because artificial variables are dummy. They're just a modeling trick that you're using in order to find that initial solution. They are not representing anything in your problem. So you don't want them to have a value different than 0 when you solve that first phase. If you think this from a practical perspective, let's say you're solving a production problem. You're trying to decide what to produce next week. You have these constraints that are greater or equal to or equalities, and then you're trying to solve this problem by hand using the simplex method. If you bring those artificial variables, they're not representing anything in your production problem. They're just there to help you find an initial solution to that problem so you can solve the problem. So that's why we just want to use them to find that initial solution and then remove them, because they are not representing production, they are not representing resources, they are not representing your volume of production for next week. They're just there as a modeling trick for finding that initial solution to solve the problem. So from a mathematical standpoint, basically, if you look at the graph, and we have, again, this is the only way I can explain it is by looking at 2 dimensions. But this applies for 3 dimensions, 4 dimensions, 100 dimensions. So we have a visible region. Let's say this is a constraint that is greater or equal to. This is a less than or equal to constraint. And then you have a visible region that is here. So basically what you're trying to do is, if you have these type of constraints, is I don't know where to start my search. I know I have multiple options here, but I don't know where to start my search. So these artificial variables, basically what they're trying to do is, okay, find a point so you can start searching for the optimal solution. So it's finding one of those corner points so you can start your search and find the optimal solution for your problem. And that also applies, like if you have, if I can draw this, 3 decision variables, X, so in that case, you have X1, X2, X3, and you can have, like, your constraints are now planes. And then it could be another plane going in this direction. So you have all those planes intersecting, and you're trying to find out where to start finding a solution for your problem. If you get this to a 4 dimension, this will become a very, imagine 100 decision variables, you have all these planes crossing. So you are trying to find an initial solution for your problem. And then start using the simplex so you can search this whole space, all these planes crossing, to find an optimal solution. Yes.
Well, like in real life, after you do this, like consultation, you get all the way up to like 100.
Yes. There are problems that, for example, problems like the travel salesman problem in which, for example, if you're planning your route for Amazon or you're planning a route for picking up trash in the city, those are called traveling salesman problems. And those have million variables and a lot of constraints. So you have to formulate the constraints for every possible route that you can have in your system. Like if you have 1,000 homes and you're picking up the trash and you have different streets, then your problem must accommodate constraints for every feasible route for your system. So let's say you start in a community and then you move to another community and then you move to another community. But it could be that you start in this community and then move to this community and then to this community. And inside those communities, you have all these possible streets that you can go to, the direction in which you go. So we're going to talk about the transportation problem in the third phase or the third part of this class, and we will touch on that. But yes, software like Ample, yes. Excel will handle certain size, but if you go to 1 million variables, yeah, you will use a very powerful computer and also a software that is designed for those purposes, like Ample. So we are talking about people that are basically focusing on this problem. That's their everyday. So they're working on finding routes every single day. These are most of the time people with graduate degrees. They are focusing on this because it's not like solving these type of problems is a done deal. There's people also doing research on this problem every day in terms of finding better algorithms, better solutions, better techniques. What if we use parallel machines to solve the problem? What if we use this type of server? So these many processors and so on. So that's why research is always ongoing, because there are problems that with the continuum of we get better technology every year, then making the best use of that requires new research, new algorithms, and that's why companies like Amazon are becoming very successful, because 10 years ago, solving those type of problems will be very difficult and almost impossible. But with the computational capability that we have right now, we're able to solve those problems quickly, and we are able to make decisions quickly. And that way they can apply those results really quick and be successful. But 10 years ago or 20 years ago, that was a dream. I mean, having those decisions made in real time. Yes.
So that for Amazon is the one has to have like master free type of product. So
yes, so that's a very good question. So so for example, they are always hiring people with operation research graduate degrees for those type of jobs. Like if you go, and most of the time at that level of planning, they're looking for people with PhD. Because what we are saying is, are you able to generate new algorithms? Are you capable of sitting down and develop new algorithms that we can use and apply in our everyday problems? So for that level of training, you will have to go through a dissertation process in which you sit down and you develop your own algorithm for a problem. And they're looking for that type of experience. But that being said, that level of people, those people will need other people as part of their group that they not necessarily have to be PhDs. I know, like if you go to Amazon, you will see a lot of openings for those types, and most of the time those are located in Seattle. So you have to go to their headquarters to work on those type of problems. I think most, I have some friends working there right now because of COVID. They can work from home, so they're located everywhere. But most of the time, they are located in Seattle. Yeah. Good questions. And they have also offices in Austin. I don't know what type of problems they're trying to solve for their offices here in Austin, but I'm sure that they have people working for those type of problems in Austin right now. And that's not only Amazon, but a lot. Austin?
Yeah, many companies.
Oh, yeah. So right now, yeah, I have friends also that they're working from home, like silicon, semiconductors, most of them that are doing design or decision-making problems, they're working from home right now. Companies are seeing that is not making a difference. For certain type of jobs, doesn't make a difference if you're there or at home working from your computer. If you're sitting down in front of the computer, doesn't matter from my point of view if you're doing it at home or if you're sitting in the office. Is that what you're doing the whole day, sitting in front of the computer coding? You can do that from everywhere. Questions? Let me see how far we are here. So let's talk about the solution for this problem. So at the undergraduate level, we go and we explain and we teach you, this is how you apply this knowledge that has been created already for you. So we teach you the simplex, we teach you branch and bound that we're gonna learn later this semester. So as an undergrad, you're basically getting all this information and you are learning these tools so you can apply them in practice. When you go to graduate school, you're basically trying to, now that you know these concepts, you're trying to find ways to make those algorithms or concept better. You want to create your own thing. That's the mindset in graduate school. So you know this simplex method, can you make it better? Can you find a way of, let's say, find a cutting plane method that will give you a solution instead of waiting 1 hour, you can find the solution in 5 minutes. And those are the type of questions that we want to answer using research. If you have a simulation model by itself, might not give you the solution you want. Can you come up with a strategy that you combine optimization and simulation and create this feedback loop that when you integrate both methods, you can get a better solution for your problem? And that's the question, research question. So now you're thinking about, let's take the benefits from this strategy, let's take the benefits and let's combine them and say, and do something new. So that's the mindset. It's not learning what's already being done. Now, as a researcher, you want to create something new. And those are the ideas that you see every day, like these people creating new software or these people creating new apps, because they come up with these ideas and then they find a way to connect those to everyday problems. Now you might think, okay, delivering food to your home. I mean, you have people doing that. Pizza delivery has been there for many years. But now you are not just limiting that type of food to being delivered to your house. Now you have all these other apps that is letting you choose which restaurant you wanna go get some food delivered to your house. So that's the yeah. I can tell you a million stories about different applications that have been developed based on just research. So this is the solution for the first phase. Check it out. Yeah, at this point, I wanted to highlight the second table. Let me turn on the other screen. Okay. So the second table here, when you do the minimum ratio test, you see that the ratio is the same. So you have to make a decision, which one are you going to take out of the tableau. As I mentioned already, what you want to do is you want to take the artificial variables out of the Tableau as soon as possible. You don't want the artificial variables to be basic in your solution, because if they're basic, they have an opportunity to be different than 0, and you don't want that. You want to make them non-basic as soon as possible, so they're fixed to a value equal to 0. So if you have to make a decision like this one between an artificial variable or another type of variable, you want to take out the artificial variable. So that's what we did here. We want to remove R2 and we want to enter X2. Yes. Yes.
First one, for the very first table.
Yes.
For R2, you use -1.
Yes. Oh, yes. So remember that before you set up the Tableau, you had to move the decision variables to the left, and that would change the value of the objective function coefficient.
Would you add
Going back to this, we have the minimization of R equals R2. So now you're making the objective function. So this will be negative.
negative like there because become optimization?
The objective function is always minimization for phase 1.
Also,
And it doesn't matter if it's maximization or minimization, when you move them to the left, they'll become negative.
and why is it not?
Because the coefficient for R, this is like saying 1 times R. So the coefficient that you want to put in the Tableau is -1.
So is it M?
M is for the M method. So in this case, every time that you have a decision variable by itself, the coefficient of that variable is 1. It's like saying you have 3x1, you know the coefficient is 3. But if you have x1 by itself, the coefficient is 1. Okay? Yes. Artificial? Yeah. So and they have the same ratio. You pick one of them. The decision is made if you have to decide between an artificial and non-artificial, you always select the artificial. But if there are two, then you pick either one.
For S1, we put 0, we not put 1 as a
F1 is a slack and it's not part of the objective function. So that's why it's 0 here. F1 is not part of so that row 0 is only the coefficients for the objective function. So the only variable that is part of the objective function is R2. So that's why in row 0 you have a coefficient of -1 for R2.
For E, we have that.
Well, this is after the first iteration. So the Tableau that you're looking at, the initial Tableau is the one at the top. Negative for this one? Oh yeah, so that's for solving the problem. So we want, let's see. So we are entering X2. R2 is leaving, so we have to make this 0, 0, 1. So we multiply this by -4 and we add it to X2, to row 0, I'm sorry.
It's like divided.
Divided by 4 first, so you make it 1. And then to make this 0, you have to multiply this by -4 and add it to row 0. And then to make this one 0, you multiply this by -1 and add it to row 1.
The one more time, just -4, you multiply by 1
-4, you multiply that by 1, and then you add it to row 0. Yep.
That's all for the first phase. Phase one.
First one, yes, phase 1. That's phase 1. Yes. So now when you get to this point, you have to observe, like right now, you don't have any positive coefficient, everything is 0 and negative, so you're done. This is the optimal tableau. So you have to double check your solution. In this case, artificial variables are out, so that means that this has to be 0 because artificial variables are non-basics, so they're equal to 0, so they have to be 0, and that's the solution. If for some reason you get to the optimal solution and you still have an artificial variable here that is different than 0, what that means is that the problem has no optimal. It's undefined. The problem has it doesn't have a feasible region in which all constraints are satisfied. Okay, so an artificial variable in this optimal tableau, an artificial variable with a value different than 0, basically what it's representing is that you have no solution for that problem. Yes.
On the second tableau, why are we repeating R and R2?
Here.
Yes.
Okay, so you see that first table? When you look at R2, you have a -1 at the top. So before you apply the simplex method, you have to make sure that that -1 is changed to a 0. So you have to apply the elementary row operation. Right? You want the identity matrix in your problem. So the basic variables are S1 and R2. So you see S1 is 0, 1, 0. So it has a 1, and then the rest of the column is 0. But for R2, you have a 1 and 0 and a -1. And that needs to be formatted in terms of zeros and ones. So you have to make that -1 equal to 0 before you apply the simplex. You have to make the tableau consistent. That's what I'm being reminding you. So before you apply the simplex, you have to make that tableau consistent. Because if you look at the solution for this problem, it's saying that R2 is equal to 8. But if you look at the objective function, then if R2 is equal to 8, then the objective function value should be 8 as well. And the tableau is not representing that. What the tableau is saying is the objective function value is 0. The reason for that is because that column for R2 is not consistent. You have to make that equal to 0. At the top, you make that equal to 0, you see how this changes to 8, which is the actual solution for the problem at that point. So what you need to remember is, for two-phase method, for phase 1, so for phase 1, you formulate your phase 1 by first setting up the problem into equation form and adding the artificial value, and making sure that you have the right objective function for phase 1. So once you have that, you set up your table. This is the initial table. Now you have to check if this table is consistent. So you look at your basic variables, S1, yes, 0, 1, 0, that's good. You look at R2, -1, 0, 1. This is giving you a flag. This has to be equal to 0. So the first operation you have to perform is to make that equal to 0. So you perform the elementary row operations here. You multiply this by 1 and you add that to row 0. That's going to give you the tableau here. And at this point, then you can apply the simplex. You apply the simplex method. One iteration, you get the optimal solution for phase 1. This one. So now you have the optimal solution for phase 1. you need to go to phase 2. Yes.
So is this row 0 I? Like it's just a row for just method, yeah. Like just zeros. Go.
This is the result for the iterations.
No, but I mean the first table we started with row 0 as I.
Yes.
Is all zeros.
All zeros and a -1 for R2.
So this is like for typical for
For the phase 1 of phase or two-phase method. For phase 1 of the two-phase method. Yes. Yes.
So that's on R2, our base there.
At what point? In the beginning, S1 and R2 are going to be the basics. So they have to represent the identity matrix. Yes.
The very last one on the very right side, you said that you just multiply 984.
So this is just to represent how we got to this 0. So which is multiplying this by -4 and add it to row 0. You don't have to include that in the solution. This is just for
Just for like
explanation. Yeah. So now you take the coefficients from this optimal solution to the new phase 2 tableau. So you will bring back the objective function, the original objective function, and you bring the coefficients from that tableau. You eliminate the column for the artificial variable. And again, now that you bring the coefficients for the objective function, the original objective function, you have to make sure before you apply the simplex method that this tableau is consistent. So your S1 and X2 are your basic variables. So if you look at X2, this column is not representing the identity matrix. And for S1, we're good. So we need to make sure that this is 0 before we apply the simplex. So how do you make this equal to 0? You multiply this row by 2, and then you add that to row 0. Which is giving you this tableau. See, you now have this in the right format. You have S1 in the right format. So now you can apply the simplex method. So for maximization, we look for the largest negative coefficient. So in this case, that's -3. So we're going to enter X3. We do the minimum ratio test. Right-hand side divided by the coefficients of X3, you have 0 divided by 1/2, that's 0. Then you have 2 divided by 1/2, that's 4. So the minimum is 0. There's a difference of dividing 0 by 1/2. It's not the same as dividing 2 over 0. So this is the numerator, and that's valid. 0 over a greater or equal to 0 number that is defined. That would be equal to 0. So X1 is leaving, X3 is entering. So this column now has to be transformed to this column. So after performing that iteration, we have X3 now in the format of S1. So we got the optimal solution. There's no negative coefficients in row 0. So the optimal solution is X3 equals 0, X2 equals 2, and the right hand, the objective function value equals 4. Yes. Here? Oh, that's a good question. Like, but at that point, you're not sure of whether or not you have achieved the optimal solution because of the way the algorithm is designed. You have to complete the iterations to make sure. So basically, that extra step that you're performing is to make sure that there's no other coefficient that is negative, and that you have found the optimal solution for the problem? That's a very good question. And you see, that's a research question right there. So can we stop as a step before and save that computational time? It's a good question. Yes.
How can this be applied to like small business?
Small businesses. Yes. So what we are teaching right now is just a way to solve any linear programming model. So how would you apply this to small businesses? It depends on what question you want to answer. So it will start with the formulation of your problem. So if you have a specific problem, a decision-making problem, then we can formulate that mathematically, like we did in lecture 3. And then we can apply these methods to solve that problem. So this piece right here that we're discussing in the second part of the course is teaching you how to solve any linear programming model. So this could be applied to any linear programming model based on the formulation of your problem. That's what's going to determine what you're going to be solving for, right? So the formulation itself, once you have the formulation, then you can apply this to solve that problem. So small business decisions in terms of what to buy next. What's your current inventory? What will be the minimum inventory that you might keep in your business? The scheduling for your staff. If you have a decision in terms of opening more stores, all those questions can be answered using linear programming. Yeah. So any decision-making question, and that's why these methodologies are becoming very popular in management science and so on, because they allow you to answer questions with data. And now data is becoming available. Like you can get any data that you need. You can formulate your problem, insert the data, and get a decision based on the solution. Yes.
Define the solution for X1.
The optimal solution for
X1.
X1? Yeah, the question is, did we find the solution for X1? So remember that if they're basic, the solution is listed here.
Yeah.
If they are no basic, they're equal to 0. If they are not part of this group, they're always equal to 0. And you can input this solution into the original formulation. Like if you go back to the original problem and you enter x2 equals 2, x3 equals 0, and x1 equals 0, you'll see that that solution meets the constraints. And yeah, gives you a value of 4. Like the objective function was 2 times x2, so 2 times 2 is 4, so that's what we obtained. And then I don't know if I can see the constraints here. Yes. So it's 2x1 plus x2 plus x3 less than or equal to 2. So x2 equals 2. Right? It's not clear here at the top, but the original constraint is 2x1 plus x2 plus x3. So if you make x2 equals 2, that's meeting the less than or equal to constraint. And then 3x1 minus plus 4x2 plus 2x3 greater or equal to 8. 4 times 2 is 8. It's meeting that constraint greater or equal to 8.
Have three unknowns. One of the x will be 0 anyway.
Well, if you look at the way the problem is formulated, yes, it has to, if you choose to make, or the decision is saying that x2 is going to be equal to 2, then the rest has to be equal to 0, because that's the only way you will meet the constraints.
That's we will find at the end.
That's what you find at the end, after solving the problem.
Before we solve, we can say that since we have 2 constraints, the unknowns, the one of the unknowns will be anyway 0.
Well, I see what you're saying. This is something that you can try to figure out by looking at the constraint, because it's a small problem, and that's right. But if you the purpose of the exercise is to teach you the method so you can apply it to larger problems in which you will not be able to figure out that by just looking at the constraints. I don't know if you follow what I'm trying to say.
Yeah.
Yeah, that this will not be a practical problem. This is something that you can solve with the graphical method. But the exercise is good in terms of showing you what's going on with the method. Now that you understand the method, you can apply it to any problem. Yeah. And this is something that Ample would do automatically. Okay, so if you remember in Excel, if you remember, and we're gonna go back to Excel after the second exam and to Ample. Remember for Excel, for example, if you click on the report for the answer, it will give you the values for the slash, even if you don't formulate them as part of your problem. Because what we did, we entered the constraints as they were given, include the slacks for some of them, and it will still generate the slacks for you. So they will do this process of finding the initial solution with the artificial variables automatically. Okay, so basically, I wanted to start a new topic. I guess good for you is that that will not be part of the exam. That will be moved to the next exam. So the exam will focus on the simplex and solving problems using the computer, and also finding an initial solution using the artificial variables. So those are, I think, our lectures 4, 5, and 6. Yes, 4, 5, and 6. We have the simplex, right? The first was lecture 4. We have solving problems using the computer, using Ample, and using Excel. And we have lecture 6, which is the M method and the two-phase method. Simplex, yes. We were solving problems that were less, constraints that were less than or equal to. So for those, you didn't have to use the artificial variables. You remember all the constraints were less than or equal to, so we were adding slacks and we were finding the initial solution with the slacks. But then we transitioned to solving the problem with the computer, and then we discussed the artificial variable methods to find the initial solution for problems that the constraints are not less than or equal to always. After the exam, we're going to start discussing sensitivity analysis. And if you have an interest in business, that sensitivity analysis lecture is very, very interesting for answering questions. If you do this, what will happen? If you do this, what will happen? That's coming after the second exam. Okay. Good. So we'll talk more on Monday. Have a good weekend. And yes, go ahead. No, just the document that you completed in class. So make sure that you take a picture and upload it to Canvas. No. So it's stating the Excel solution. Yes, you don't have to submit the Excel file. Just submit this. I was asking you to just look at the Excel to verify your solution, but yeah. Okay, this. In the review on Monday, we're gonna go back to the lectures, which is what I just mentioned, 4, 5, 6. And then we're gonna talk about the homework assignment problems. We can look at them, and also about the format of the exam. Yeah. Okay. Any other questions? Oh, good. See you Monday.